Ever wondered how LLM like ChatGPT and Claude work under the hood? Like what is actually happening when you type a message and it responds so intelligently? Today we are building something that I wanted to build for a while. That is coding the paper Attention is All You Need from scratch. This is the paper that changed everything in AI. It introduced transformer architecture, which is the foundation for ChatGPT, BERT, T5, and every other large language model you ever known of. To truly get the grasp of modern AI, you need to understand this paper. Hello everyone, welcome to the channel. Here what we are going to do today. I have this architecture diagram on the screen, and this diagram is going to be our North Star for the entire video. We are going to go through it piece by piece, exactly the way data flows through the model. And for each piece, the pedagogy of this video will be the same. I will explain what it does intuitively, and then we immediately write the code. By the end, we will have a working transformer that you can actually train. So let's get started. Look at the diagram. The overall architecture has two main halves, the encoder and the decoder. The encoder on the left, it takes the input sequence like how are you and processes it into a rich context-aware representation. Think of encoder as the part that understands your input. The decoder on the right side, it takes the encoder's output and step by step generates the output sequence, like "aap kaise ho" in Hindi. Think of decoder as the part that generates the output. But here's the key insight, and this is what makes the transformer revolutionary. Instead of using RNNs or LSTMs to process sequence step by step, the transformer uses self-attention mechanism to look at the entire sequence at once in parallel. That's why it trains so much faster and why it can capture long-range dependencies that RNN struggles on. Now look at top level diagram. You can see that both encoder and decoder are actually stacks. In original paper, there are 6 encoders and 6 decoders stacked on top of each other. Each encoder is identical in structure, but they don't share weights. Same goes for the decoders. Now before we move forward, I would like to take few minutes to discuss what came before it. Because discussing that will help us understand each and every decision taken during the designing of Attention is All You Need paper. Now I have this diagram on the screen which the transformer is trying to replace. As you can see on the bottom, this is the encoder which is a chain of LSTM cells, and similarly we have on the top the decoder which is also a chain of LSTM cell. Now each LSTM cell are connected sequentially both in encoder and decoder, and each and every one of them takes one token at a time and gives an hidden state one at a time. So for example, like H2 cannot be processed until H1 is processed, and H3 cannot be processed until H2 is processed, and so on and so forth. And in the decoder part, we also have the hidden state of S0, S1 and S2, which is also getting sequentially processed. It also takes a context vector as an input. We will talk about it more shortly. Now this purple bar is basically time distributed dense layer, which calculates this attention score on every decoder step. And this is basically the weighted sum, like it outputs the weighted sum of the hidden state from the encoder and the attention score, basically telling on each score like what matters most for that particular step. And also we pass in the hidden state previous hidden state of the decoder, so that the model basically is saying that I know this much about it, what would be the next appropriate token for me, and then it outputs the answer. This paper was state of the art of that time, but there were some drawbacks, like it doesn't process the tokens parallelly, which increases the training time, and it also get a lot of load on GPU. And secondly, even though we have this purple bar as attention mechanism, but this context vector is still a bottleneck, because we are providing it a compressed version of the entire source, which again like creates the problem and also the third drawback of the vanishing gradient, because as the sentence or the data set increases, the size of the sentence increases, the context vector will only remember the recent bits of it and not the what happened in the past. So to resolve all this, the transformer paper was introduced, and now we will look at what it is and how to build it. One last thing before we dive into the architecture, let's set up our project. So I will start by importing. So I will start by adding some import like import torch, import torch.nn, and import torch.nn.functional as f. And one final thing is import math. And I will also set the manual C to 42 so that every time the random weights are initialized, they are reproducible. And I will also initialize few constants like dimension of the model as per the paper which will be 512, and number of heads which will be 8. This will make more sense once we discuss the architecture, but for now bear with me. And number of feed forward inner dimension, number of layers, dropout rate, and finally max sequence length for the positional encoding, which will be 5000. And that's it. I think we are ready to build the architecture. Okay, now the first block is the input block. In that, the first thing that happen is we take raw text and turn it into numbers. There are two steps for it. First is tokenization and the second is embedding. Let's discuss tokenization first. So in tokenization, the sentence is split into smaller units called text. In the diagram, you can see the how are you text gets split into 3 different tokens called simply how, are, and you. In practice, real transformer use subword tokenizers like byte pair encoding BPE, which is what GPT uses, or word piece, which BERT uses. For our implementation, to keep things clean and focused on the architecture, we will build a simple character level or word level tokenizer. The architecture doesn't care about the tokenizer details, it just needs a vocabulary and integer IDs. So let's build this our tokenizer first. Okay, now let's start coding our tokenizer. We will create a class named tokenizer, which will have obviously init function, and in this we will have 2 dictionaries. One is word to index and the other is index to word. So these 2 dictionaries basically are required for the mapping of string and integer ID. So word to index maps a word string to an integer ID, and index to words does the opposite. We need both directions, one for encoding text into numbers before feeding it to the model, and one for decoding numbers back into text when we want to read the model's output. And one more variable will be basically vocabulary size, initialized with 0. This will be helpful later in the model when we will be defining the linear layer. So after that, we will also have a list of spatial tokens. These will be padding, start of sentence, end of sentence, and unknown. Padding is required when a sentence is shorter than the rest of the sentences. So to have the same sequence size, we need padding, and we used to fill that sentence with the padding. And the model will learn to ignore it as we train it. SOS, as it stands for start of sequence, we prepend this to every decoder input to tell the decoder start generating now. And EOS stands for end of sequence. We append this to the every target sentence, so the model learns when to stop generating. And unknown simply handles any word at inference time that wasn't in the training vocabulary. And finally, we will go loop through this spatial tokens and then add it to our vocabulary. For that, we are using a helper function called add token. We will write it next. Okay, now let's write the add function. So this add token function. Add token function will take token as an input, and it will first check if a token is present in the word to index dictionary or not. And this function is basically the core helper for both init and build vocab function, which we will write next. It obviously, as I told, it first checks if the token already exists. If it does, we skip it because we never want to have duplicate records. And if it doesn't exist, we assign it to the current value of vocab size as its ID, store it in both dictionaries, and then increment vocabulary by 1. So the first token ever added gets ID 0, the second gets 1, and so on. This is why the special token always gets ID 0, 1, 2, 3, because we add them first before any real words. So let's finish this function in as I explained it. Next, we will write the build vocab method, and it will simply iterate through each and every sentence and split the words and add it to the token dictionary. And now we will write the encode function, which also takes a sentence as an input, and it will return the tensor of integer strings. Notice it wraps tokens with SOS and at the front and EOS at the end. This is the format the decoder expects. It receives SOS as its first input and learns to produce EOS as its last input. So let me finish the code for that. So we will give it a list which is like the conversion of words into the tokens. And finally, if we have to add or not a special token, so I will also have to add another parameter at top like boolean, and the AI is doing its work coding it for us. And instead of returning the tokens, we will return torch.tensors because we need the encoded version. And finally, we will give the decode, write the decode function where it takes a tensor of IDs and join them back into a string, but it filters out all the spatial tokens since we don't want those appearing in the final readable output. So it will be something like token ID as a parameter, and words, I think the AI already wrote it for us. Let me just check if it's correct. Yeah, it is correct. I have to just add that condition, like it doesn't have a spatial tokens into them. If idx dot item, sorry, it has given let's convert it to idx. Yeah, and here not in, and I think now it's taking, let me bring it down. Yeah, now it has finished the function for us. So yeah, this is how a simple tokenizer we have created on our own, but in production, like in the paper, they used, as I told previously, BP, but for now we will go with this. Okay, after tokenization, we have integers, but neural networks need continuous vectors to work with. That's where embedding came into picture. An embedding layer is just a lookup table. For each token ID, it returns a learned vector of dimension equal to the dimension of model. In this case, it's 512 dimension. So if your vocabulary has 10,000 words, your embedding matrix is of size 10,000 cross 512. Sorry, 512. These vectors are learned during training. The model figures out how to represent each word in this 512 dimension space. One subtle thing from the paper, they scale the embedding vectors by a square root of the dimension of model. This is because the positional encoding, which we will add right after, have values between -1 and 1. And without this scaling, the positional encoding would be too small relative to the embedding to have any effect. Scaling up the embeddings ensures they are on the same scale. So next we will write the code for creating these embeddings. Okay, now we are back in our file. Let's write another class called embedding, which has which inherits nn.module, which is the base class for every neural network component in PyTorch. Anytime you build a custom layer or model in PyTorch, you inherit from nn.module. It gives you parameter tracking, state dictionary saving, .to device support, and everything else PyTorch needs to treat your class as a proper model component. And okay, now post that we will write the init function, which will have vocab size, like vocabulary size, and dimension of the model as the parameters. And we will call super dot init to call the initialization method of this inherited class, or the nn.module class. And post that we will add self.embedding and nn.embedding with vocabulary size and dimension of the model. We create nn.embedding with the vocab size and d model. This is PyTorch built-in lookup table. Internally, it's just a matrix of shape, vocabulary size, and dimension of the model, filled with the random values at initialization. When you pass it in an integer, it returns the corresponding row of the matrix. So if word how has ID 4, self-embedding 4 just returns row 4 of the matrix, a vector of 512 numbers. These vectors are learned parameters, meaning backpropagation will update them during training until similar words end up with the similar vectors. We also add one more variable called dModel, which stores the dimension of the model as an instance variable because we need it in the forward method for scaling. Next, we write the forward method itself with the x as in input. Basically, x is the tensor of integer token ID with shape, batch size, and sequence length. We pass it through self-embedding, which does the lookup and return shape of batch size, sequence length, and dimension of the model. So every integer ID has been replaced by its corresponding 512 dimension vector. Then we immediately multiply by square root of like dimension model, which is like square root of 512 in our case. As we discussed earlier, this scaling ensures the embedding are on the same magnitude as the positional encoding that we are about to add. So neither one drowns out the other. So to finally complete this, we will just simply multiply all our embeddings with the square root of the dimension of the model. And that's it. That's our simple embedding model or embedding class, we can say. Now we have embeddings, but there is a problem. The self-attention mechanism we are about to build treats token like a set. It has no built-in sense of order. If you shuffle how are you and are you to are you how, it would produce the same output without positional encoding. That's obviously wrong, as word order matters enormously in language. The solution is positional encoding. In this, we add a special vector to each token's embedding that encodes its position in the sequence. After adding, the model can figure out both what a word is from the embedding and where it is from the positional encoding. Look at the formula in the diagram. It has like sine and cosine of angles which are defined by position and the index of the dimension of the model and the dimension of the model itself. So here the pos is the position in the sequence like 0, 1, 2, 3, and I is the dimension index, which goes from 0 to half the size of the dimension of the model. So for each position, we compute a vector of sine and cosine values at different frequencies. The frequencies decrease as I increases, so low dimensions oscillate quickly, capturing local position, and the high dimension oscillates slowly, capturing global position. Why sine and cosine specifically? Basically, the author chose these because of nice mathematical property. The positional encoding for position, let's say pos plus k, can be expressed as linear transformation of the encoding for the position pos. This means the model can easily learn to attend by relative position. So like if we want to reach to position 3, we can simply add a pos plus some value to reach the next position. Also note that in the diagram, this tilde sign, it means the positional encoding are not learned. They are fixed mathematical functions. This means the model can generalize to sequence lengths it hasn't seen during training. So now let's code this positional encoder. Now we create a class called positional encoding, which also inherits the nn.module, and we will first again initialize the class with the parameters like the model and dropout which will be by default 0.1 and max length, which is in our case 5000 default. And again we will call the initialize method of the parent class, and in the init method we also create a self dot dropout, nn.dropout, and give it the argument which we passed during the initialization, that is a dropout. We apply this at the very end after adding the positional encoding. It is a regularization step to prevent the model from over relying on specific positional signals during training. Now we create an empty positional encoder matrix, a blank matrix with p.torch dot zeros and with arguments like max length and d model. This is going to hold the pre-computed positional encoding for every possible position up to max length. We compute this once upfront rather than on every forward pass because the value never change. They are fixed math, not learned parameters. and then we give a position equal to torch.arrange 0 max and d type with unsqueeze 1. So basically gives us a column vector of shape 5000 comma 1 containing 0 values from 0 through 4099, just the position indices. The unsqueezed one adds a dimension so it broadcasts correctly against div term in the next one. Div term is basically divisor term. Now for the div term, or basically the divisor term, we want to compute 10,000 raised to the power of 2i divided by d model for dimension index I. But instead of computing the exponent directly, we compute it in log space using like torch.exp torch arrange 0 d model and d type float, and we multiply it by the negative log of 10,000 divided by d model. This is mathematically identical but numerically more stable. Large exponential can overflow in floating point. So taking the log first and exponentiating after keeps the value in safe range. The result is a vector of shape d model divided by 2, which is 256 in our case, one divisor value for each pair of dimension. Next we apply sine to even indices and cos to odd indices. The 0 colon 2 slice means start at 0 step by 2, so column 0 to 4 6, and similarly fills the column 1 3 is 5 7 for the cosine values. Because position is 5000 comma 1 and div term is 256, PyTorch broadcasts them together to produce a 5000 comma 256 matrix, exactly the right shape to fill half the column of the PE. After that we call PE unsqueeze 0 to add a batch dimension, making PE shape 1 comma 5000 comma 512. The one at the front means it will broadcast across any batch size in the forward pass. Finally, we and this is important, we call self.register buffer PE comma PE instead of nn.parameter. This is a PyTorch distinction worth understanding. nn.parameter registers something as a trainable weight. It shows up in the model parameters and gets updated by the optimizer. A register buffer registers something as a non-trainable tensor. It doesn't get updated during training, but it does get saved with the model when you call torch.save. And it moved the correct device when you call model.toDevice. Since our positional encoding are fixed math and should never be trained, register buffer is exactly right. And finally, we will now define the forward method for this. It again takes the x, which is of the shape of batch size, sequence length, and demodel. We add self.p colon x size of 1. The slice of x dot size 1 is crucial here. Our PE was pre-computed for up to 5000 positions, but the actual sequence might only be 10 tokens long. So we slice out only the first sequence length positions rather than adding the full 5000 position matrix. Then dropout is applied to the sum before passing it forward. And that completes our positional encoding class. Let's move on to the next one. Now we have covered up till here, which completes our input block. Now we have to move to the encoder part of the architecture. So the encoder part consists of two main blocks. One is self-attention and one is feed-forward neural network, as you can see in the diagram as well. So Yeah, I know that it says multi-head attention, but we will come to that later. Basically, multi-head attention is a collection of self-attention layers. In this case, the paper used 8 attention heads. So let's first see what is self-attention in this case. Okay, this is the most important part of the whole video. This is the mechanism that makes transformers work. Everything else is just scaffolding around this. Let us first understand this intuitively before looking at or understanding this architecture diagram. Imagine you are reading the sentence, the animal didn't cross the street because it was too tired. What does it refer to? It refers to animal, not street. When you read it, your brain is paying attention to the word animal across the sentence. That's exactly what self-attention does for every word in a sentence. It looks at every other word and asks how relevant is that word to understanding this word. It then creates a new context-aware representation by taking a weighted sum of all the other words' representations, weighted by their relevance. Now let's look at this diagram and understand what's happening here. Okay, here's how it works mechanically. For each input token, we create 3 vectors, Q, K, and V. Basically query, key, and value, where query is what I am looking for, and key is what information do I have to offer, and value is what is my actual content. But here is the question. Why don't we just use the raw embedding directly to compute attention? Why do we need Q, K, and V at all? This is actually one of the most important things to understand. Let me explain. Think about what we have at this point. After the embedding and positional encoding, each token is a vector of 512 dimension. These vectors carry meaning about what the word is, but they are completely general. The embedding for how is the same whether you are doing translation, sentiment analysis, or question answering. It has no knowledge of the task it's being used for. Now, if we directly use these raw embedding to compute attention score, dot product of embedding of how with embedding of R, the attention pattern we would get would be general task agnostic pattern, driven purely by word similarity in the embedding space. The model has no way to specialize how it attends based on what it is trying to learn. That's exactly why we introduce the weight matrix WQ, WK, and WV. These are learnable matrices initialized randomly at the start of the training. By multiplying the raw embedding through these matrices, we are projecting each token into a task-specific space. WQ learns to project tokens into a space where what I should look for makes sense for the specific task. WK learns to protect tokens into a space where what I offer to others makes sense for this task. And WV learns to project tokens into a space where what information I carry is organized for this task. So QKV vectors are not just the raw embeddings. They are the raw embeddings transformed by learning weights, so that the attention pattern becomes task specific. Without these matrices, every task would attend to words in the same generic way. With them, the model can learn completely different attention patterns for translation versus question answering, even on the same sentence. And critically, at the starting of the training, WQ, WK, and WV are initialized with random values using Xavier initialization. They start knowing nothing. Over thousands of training steps, backpropagation adjusts these weights so that the attention patterns that emerges are actually useful for the task. That is what learning is in the self-attention. Without WQ, WV, and WK, we just use XHOW directly for all 3 and get a generic task agnostic attention pattern, not what we want. This is the reason there are 3 separate weight matrices and not one. Query and key need to be in the same space so their dot product is meaningful, but value can be in different space. it's what gets aggregated, not what determines how much to aggregate. Now, if you look at the diagram here, you can see how and R each produce their own Q, K, and V vector through WQ, WK, and WV. In the original paper, with 8 attention heads and a dimension model with dimension 512, each Q, K, and V vector has dimension of 64. That is simply 512 divided by 8. That's the 500 cross 64 matrix you see in the diagram. Then after that, we move forward to getting the computing the attention score. We do it by calculating the dot product between the Q and K vector of token I and J. For example, this S11 in the diagram is the dot product between Q how and K how. How is attending to itself in this, and S12 is the dot product between Q how and K r. Here it's attending to the vector r. Now here is a subtle but critical problem. Let's think about what the dot product actually does statistically. Assume the components of Q and K are independent random variables with mean 0 and variance 1, which is roughly true after random initialization. The dot product of Q and K is a sum of dimension K such products. Each term Qi and Ki has mean and variance 1. Since we are summing d of K, like dimension of K independent terms, by the variance addition rule, the total dot product has variance of dk and standard deviation of square root of d of K. So as dk grows, and in the paper dk is equal to 64, the dot products don't stay small and well behaved. They grow in magnitude proportional to square root of dk. With dk equals to 64, your dot products have a standard deviation of 8. This means you will regularly see scores like plus 20, minus 15, plus 18 sitting next to each other. Now feed those large values into the softmax. That will give values like 0.88, 0, and 0.12. The softmax becomes extremely peaked. Almost all probability mass collapses onto one token, and everything else gets driven to near 0. This is called the saturated region of softmax. And here's where the vanishing gradient problem comes in. During backpropagation, the gradient flowing back through softmax depends on softmax into 1 minus softmax. When softmax is saturated, outputting values near 0 or 1, this product approaches 0. The gradient essentially vanishes at the softmax. That means the weight matrices WQ and WK receives near 0 gradients and barely updates. The very weights we need to learn to make the attention task specific, the one we just discussed, stop learning. Training stalls. So for this, the fix is beautifully simple. We divide by square root of d of k before we apply the softmax operation. This is also called scaling. Now dividing by square root of dimension of k brings the variance back to 1 regardless of how large a dimension of k is. Now the score fed into softmax are well scaled. The softmax stays in its non-saturated region, gradient flow cleanly back through it, and WQ and WK, WV actually learn. That single division is the entire reason of the word scaled in the scaled dot product, attention. Then we apply next is the softmax to get attention weight that sum to 1. Finally, we compute the output as weighted sum of values. We multiply each weights with the v how vector, and then take a sum of all those vectors. In matrix form, the entire operation is softmax of dot product of q of k divided by square root of dimension of k multiplied by the value vector. So in the so this is what basically the paper has used. We, in a nutshell, we first take the dot product of q how and k how, then we scale it by dividing it with the square root of dimension of k to bring the mean to 0 and variance to 1, and we take the softmax of it, and finally the score we get, we multiply it by the v how or the value vector, and the final score is the final vector is the attention matrix that we want. This is the entire operation what happens in a self attention. Now let's code this in our Python file. Okay, we are back in a file. Let's write another method called scaled. Okay, AI already got the name scaled dot product, and it has obviously three different vectors: query, key, and value. These will be three different tensors, and another parameter called mask. This will be optional. This will be required in the decoder part of it. So for now, let's just leave it there. Next, the first line will be the dimension that grabs the last dimension of q, which is the depth of each query vector, 64 in this case. We need this for scaling factor. Then comes the score. Basically, we are simply doing the dot product of key and query and key, and then scaling it with the square root of dimension of k, and we store it in the variable scores. Next, we apply the masking. I will explain this why we need mask when we come to the decoder part of the architecture. For now, we will just keep it here because we will be using the same function in the decoder as well. So here, as the mask is optional, we first check if it has a mask, then we apply the mask to the score. Next, we then apply the softmax along the last dimension, the key dimension. This means for each query position, we normalize across all key positions, so the attention weights sum to 1. The dimension or dim equals to -1 is important. We want each row to sum to 0, not each column. Yeah, after that, I missed one thing. We compute the attention. We apply actually a safety net to the attention weights by using torch dot nan to number and attention weights, and we will replace the not a number with 0. This is for if an entire row of scores was negative infinity, meaning a query had no valid keys to attend to at all. Softmax would compute 0 and produce not a number. This line replaces any NaN with 0, so the computational doesn't silently corrupts everything downstream. In practice, with correct masking, this shouldn't happen, but it is a good defense. Okay. Finally, the output computes the weighted sum of values, attention weight, and into multiplied by the v vector, and multiplying them for each query position, we get a new vector that is weighted blend of all value vectors, where the weights come from how much that queries attend to each key. We finally return both output and attention weights. The weights are not needed for the forward pass, but they are invaluable for visualization later when we want to see what the model is actually attending to. And that's the simple scale dot product or self attention, you can say, in the code form. Let's move on to the next one. Okay, now that we understand the self attention, but in the architecture, as you see, it says multi-head attention. And as I told you previously, like multi-head attention is basically stacked version of 8 self-head attention as in the paper. So let's understand what multi-head attention is. With the single attention head, the model can only attend to information in one way, one type of relationship at a time. By language, but language has multiple types of relationship happening simultaneously. For example, in the bank by the river was steep, the word bank needs to attend to river to solve its meaning, geographically sense, not financial sense. Attend to steep to understand what property is being described, and attend to positional context. With 8 attention heads, the model can learn 8 different types of relationship in parallel. Here's how it works. Let's look at the diagram. Here's how it works. We project the full 512 dimension into subparts of 64 dimension. And we then run scale dot product attention independently in each subspace, so that each head gets its own WQ, WK, and WV. Then we concatenate all 8 heads output, which again makes the vector size of 512. Now let's talk about why the final W not projection exists. After the step 3, you have a concatenated vector of 512 dimension. But think about what the vector actually is. It's just 8 separate chunks of 64 dimensions sitting next to each other. Head 1's output occupies dimension 0 to 63, and head 2's output occupies dimension from index 64 to 127, and so on. They have never talked to each other. No information has crossed the boundary between the heads. Each head independently decide what to attend to and produce its own 64 dimension summary. But what if the most useful signal for predicting the next token requires combining what head 3 noticed with what head 7 noticed? With just concatenation, that cross-head interaction is impossible. The dimensions are isolated. The WO or W naught matrix of shape 512 by 512 is fully connected linear layer across all 512 dimensions. Every output dimension can now be a mixture of every input dimension, meaning information from head 1 can combine with information from head 5 in a single learned linear transformation. It's the step that lets the model say head 2 found a syntactic relationship and head 6 found a semantic relationship. Together they mean something specific. There is a second reason too. Each head was operating in its own 64 dimension subspace defined by its own WQ, WK, and WV matrices or weights. The values from different heads live in a different learned subspace and are not directly comparable. The W naught projection remixes and re-expresses everything back into a single coherent D model, like dimension of model 512 space, that the next layer, the feed forward or the next encoder layer expect to receive. So W naught does two things at once: mixes information across heads and projects back into a unified representation space. Without it, multi-head attention would just be 8 independent attention heads whose outputs never interact, which largely defeats the purpose of having multiple 8 heads. So W naught does two things at once. First, it mixes information across heads and projects back into a unified representation space. Without it, multi-head attention would just be 8 independent attention heads whose output never interact, which largely defeats the purpose of having multiple heads. Now, as you look at the diagram, you can see head 1 and head 2 run in parallel. Head 1 computes yhow1 and yr1, and head 2 computes yhow2 and yr2. Then they are concatenated and projected through the final linear matrix, which produces the final output z. This z is then what is passed forward into the next step. Before moving on to that, let's code this multi-head attention now. Okay, now let's create the class for multi-head attention. We will inherit with the nn.module, and and then we initialize the class. It will have the dimension of model, number of heads, and dropout rate, sorry. By default it will be equal to 0.1. And again then we call the constructor of the inherited parent class. We then AI added an additional statement here, like if the dimension of model is divisible by the number of heads, and if it's divisible then only we move forward. We can skip this, as we are implementing in this paper, we know that it is divisible. Then next we define three variables. One is the dimension of model and number of heads, and this is the dimension of k, you can say, which is basically d model divided by number of heads. Then the three matrices, WQ weight matrices, WQ, WK, and WV. These are the linear projections for QKV, one per head, but implemented as a single big matrix. And finally, the output projection of W underscore O. And finally, the dropout layer. Then we will define another method called split head. Remember where we split the 512 vector dimension into 64 dimension vector. So this function will do that. It will split the last dimension into n head, comma, and d underscore k dimension, and transpose for parallel attention. So let's write this function. It will take x as the tensor, and it will return the torch tensor. So here the batch size and the sequence length and the dimension of the model will be the x size, like the size of this vector which we have passed, tensor which we have passed. And then finally we we reshape the vector to batch size, sequence length, number of heads, and d of k. Batch size, sequence length, and number of heads, and d of k. And we then transpose it, so we can write it in a different line as well. Return x dot transpose. This let us apply batch matrix multiplication independently per head. And moving on, next we will write the forward method, which will take the query key value vector and the mask as optional. And again it will first have the batch size. So we after the batch size we have this query key and key value, that is after splitting these into 64 dimension. So this is what these key, query, and value vectors are representing. Then we also apply the check of mask here. This will also be useful in the decoder part. So right now we have to just right now we can just write the code and move on. I will explain it later when we reach the decoder part. Next, we call the scale.production attention, that method we write for self attention, and we pass the query key value vectors and the mask, and we assign it to attention weight and output to the x. And again we do x dot transpose to multiply again for the multiplication, and then we reshape it to this shape of batch size, sequence length, and dimension of the model. And finally the linear projection, that is self dot w of o, and we give the attention output, the vector to it, and we return it as a tuple, the output, and the attention weights. Weights are important, and output is just for the visualization part. So yeah, this is the class we wrote for the multi-head attention, and next we move forward to the add and normalization after the multi-head part. So let's focus on that. Two things that are crucial in the entire architecture, either it is encoder or decoder, is the layer normalization and these arrows. Like these are called skip connections or residual connections. So we will discuss these once, and then we can just apply as it occurs in the architecture. So basically what residual connection is, if you look at the plus sign in the diagram, let me zoom it a little bit. Yeah, these ones, these are like residual connections, also called skip connections. Instead of just passing the output of the sublayer forward, we add the input of sublayer into its output. So basically, before whatever we did before the multi-head attention, these embeddings, we pass it on to the output, and they get added before passing it on to the normalization layer or block. Why we do this? Because there are two reasons for it. First one is gradient flow. In deep neural networks, gradients can vanish or explode as they backpropagate through many layers. Adding the identity, the skip connections, give gradient a highway to flow back through, making training much more stable. Second reason, representational efficiency. It's easier to learn small corrections to the input than to learn the entire transformation from scratch. These small corrections are called residuals, hence the name residual connections. So this is just the simple addition of two vectors before passing it on to the normalization layer. Now second, after the residual addition, we apply layer normalization. Unlike batch normalization, which normalize across batch dimension, layer normalization normalizes across feature dimension, the 512 dimension, for each token independently. Why layer norm instead of batch norm? Because in NLP, sequences have different length, and computing statistic across a batch of variable length is tricky. Layer norm works on each token independently, so it's much clearer. The paper calls the full pattern add and norm, and add the residual, then normalize. So basically in the layer normalize, if we do not use layer normalization and we use batch normalization, and if we fill in for the shorter length sentences, it will be filled with 0, and our vectors have zeros, a lot of zeros in as their value. We have seen in the past that it leads to a vanishing gradient problem, as the softmax then depends or highlights the larger values. So the model won't learn anything. That's why we use layer normalization. So let's implement these two, the layer normalization and the residual connection. Okay, we are back in our file. Let's create the class for layer norm. And again, it will inherit the nn dot module. So here in the init function we have gamma and beta, which are the learned parameters. Gamma is the learned scale and beta is the learned bias. And EPS is basically a safety net for our maths operation, like to prevent the division by zero during the layer normalization. Then in the forward method, we take the mean and the standard deviation, and we then do the layer, apply the normalization formula and multiply it with the learned parameters gamma and beta. So this normalization is done across the feature, not the entire set. Next, we create the sublayer connection module. Again, it inherits the nn module, and inside the init function we again call the constructor for the superclass, and we define a layer normalizer. We create an object for layer normalized class with dimension model, and also create a dropout layer. And in the forward pass, as seen in the diagram, we just add the previous vector with the newly generated vector, as you can see here in the return function. So that's it. That's the whole add and normalize thing. We wrote it first so that it can be used in different at different places in the architecture. The next we will write or discuss about is the feed forward neural network, which is the second component in the encoder part. And after that we will be done with the encoder, and we will move on to decoder. So let's move on to this. So after the multi-head attention, each token passes through position-wise feed forward network, and here's the keyword you should focus on, that is position-wise. This network is applied independently to each token. The same network, same weights applied separately to each position. It's a simple two-layer, multi-layered perceptron with a ReLU activation. The inner dimension expands from dimension of 512 to 2048, which is the 4 times. Then contracts back to 512. Look at the diagram. You can see exactly this, like 512, 2048 and 512 structure. This expansion gives the network capacity to perform complex non-linear transformation before projecting back. Why do we need this after attention? Because attention is a linear operation, weighted sum of values. The feed-forward neural network introduces the crucial non-linearity that lets the model learn complex patterns and representations. It's where a lot of knowledge in large language model actually lives. So let's write this simple component, which is feed-forward neural network. Okay, now we will again create a class, call it feed forward. The same thing, it inherits the nn dot module, and in the init function we, after calling the super constructor, we give it two linear layers, like 1 and 2, and a single dropout layer. The dimension of first linear layer will be input of the dimension of model, which is 512, and the output of the dimension of the feed forward, that is 2048. And the linear 2, that is this one, it will have the input of the feed forward, that is 2048, and output of dimension of the model. And in the forward function, it's simply we are just applying feed forward independently to each position, and the linear layer handles this automatically. So we first apply the linear, then the ReLU, then the dropout, and again the second linear layer, and we return the updated or the new vector. So this was a really simple class for the feed forward network. Let's move on. Now that we have discussed both multi-head attention and feed forward in the encoder, all that is left is we write a class to encapsulate it and not encapsulate it, maybe like group it into a single class so that we can easily instantiate it. But before going forward, just one thing: after the feed forward as well, we use the same add and norm layer which we already have written code for. So it's the same thing, like whatever we pass before passing it into the feed forward layer network, we again set up a skip connection or residual connection and add it to the output of the feed forward neural network. And then we pass it to the layered normalization, and we get the y1, y2, and y3 output or output vectors. Now these output vectors will be sent to the next stack or layer of encoder. As we discussed earlier, that the all the encoder and decoder are a stack of 6 layers. So whatever is the output, it's not the final output, it's for the second encoder layer. So let me write the class for this encoder layer, and then we will discuss it further. Okay, let's put it all together. Class encoder layer, again same thing. We define, we have a multi-head attention block, we have a feed forward block, we have the sublayer 1 that is that add and normalize layer, and the sublayer 2 that is after the feed forward, the same add and normalize. And we also need to add a dropout. Okay, so these are the two things we can yeah, let's keep it sublayer only. Yeah, and in the next function, we that is a forward pass, we take input from the previous encoder layer, and then we call the self dot attention, like to get all the attention output from the self attention vector, and we then add the layer normalization to it, add and layer normalization to it, which is we store it in X. And for the second one, we get the output from the feed forward, and again we do the add and normalization layer to it, which is in the sublayer 2, and then we finally release it. And this is a single layer for of the encoder. Now we need to write the entire this entire encoder part, which contains these 6 encoder layers. So let's write that. For that, we again go to a class, write a class called encoder, and the same thing, nn.module. We pass the vocab size, the dimension of the model, number of heads, dimension of the feed forward layer, number of layers, and the dropout multiplier or dropout rate. And one more thing, we add the max length of 5000. Now again here we pass. Oh, before that I missed one thing. In the previous class, we forgot to add the dropout layer. So let me just add it in the normalization 1. Okay, in the attention output we have to add the dropout, then we have to add it. Yes, so self dot dropout, we will pass it like this. Yep, and we will remove this. And similarly it goes same for the feed forward self dot drop out. Yep, now this is correct. Oh, yep. Okay, now we can continue here. All right, where were we? Okay, yeah, so first we will get the if you see in the diagram, we will first get the embeddings here. So self dot we already wrote the class for it, embedding. Then we get the positional encoding for it, the second step, and then sorry, we get the layers for the encoder, like 6. So number of layers will be 6 in this case. And finally we give the normalization layer. We get the object for layer normalization. And in the forward pass, we simply do like first call the embedding on the source which we are getting, the sentence. Then we calculate the positional encoding for it. We then for each layer of encoder, we pass in the x vector and get the output, and finally we normalize it. And after that, yeah, I think that is all we have to do in the encoder class. Yeah, we did the embedding, the positional encoding. We then sorry, call the encoder layer which takes care of everything, and finally we normalize the x. Okay, yeah, that's it for this. Now this is where we conclude the encoder part. We will now move on to the decoder part. So let's get on to it. Now let's begin discussing the decoder. It is a bit complex as it has 3 components, unlike encoder which had 2 components. So it has mask self attention, cross attention, and feed forward neural network. This feed forward neural network is same as the encoder, so we won't be discussing it again. One more thing before we move forward, like during the training time, this decoder behaves as a non-autoregressive, and during the inference time, it behaves as autoregressive. What does this mean? Basically, during the inference time, it generates data points in a sequence by conditioning each new point on the previously generated points. And on the contrary, during the training, it trains in parallel. It has some gotchas in it, but we will be discussing it later. Now let's first begin with the masked self-attention. There is one more thing which is different during the decoder, in the decoder architecture, contrary to encoder. Like when we supply the input to our decoder, it has to go through a write shift. Why we do that, we will discuss it when we design the decoder layer. So I just wanted to let you know that there is a difference in the input as well. Rest up till the positional encoding, everything is same. So now let's move on to the masked multi-head attention. In the decoder, we have an additional constraint when generating token at position, let's say t. The decoder should only be able to see the token at position 0 to t minus 1, like all the tokens generated before it. It cannot look at the future tokens, that would be cheating. So to solve this, we apply a mask which is also called causal mask or look ahead mask. It is a triangular matrix where position I can only attend to the position less than or equal to I. This is where things get really interesting and where a lot of people get confused. Let me explain it carefully. At inference time, the decoder is autoregressive, as I stated previously. It generates one token at a time. It produces token 1, feeds it back in, and produces token 2, feeds that back in, and so on. This is slow, sequential, one step at a time. But at training time, we already have the entire target sentence. if we are training on how are you to aap kaise ho, we have all of aap kaise ho sitting right there. So the question becomes, do we feed the decoder one token at a time during training too? If we did that, training would be devastatingly slow. You would have to do a full forward pass for a single token position sequentially. For a sentence of length 10, that's 10 forward passes. But for a dataset of millions of sentences, it's completely infeasible. So instead, the transformer does something clever. The decoder is actually non-autoregressive at training time. We feed the entire target sentence into decoder at once, all position in parallel, just like the encoder. This is called teacher forcing as well. The decoder processes all positions simultaneously in a single forward pass, which is what makes training fast. But again, we come back to that problem we have. Like if position 3 can see position 4, 5, 6 during training, future tokens it hasn't generated yet, then the model is essentially cheating. It's learning to copy the answer rather than actually learning to predict. At inference, those future tokens doesn't exist, so the model would completely fall apart. This is exactly what the causal mask solve. By masking out all future positions in the self-attention, setting their scores to negative infinity before the softmax so they get zero attention weights. We artificially recreate the auto-regressive constraint inside and parallel computation. Position 3 can only attend to position 0, 1, 2. Position 5 can only attend to position 0 through 4 and so on. So masking is what lets us have the best of both worlds. First, the speed of parallel processing during training, while still correctly simulating the sequential left to right generation that happens at inference. Without the mask, teacher forcing breaks the model. With the mask, teacher forcing trains it perfectly. So this is the only difference between the multi-head attention in the encoder and the multi-head attention in the decoder, which is the mask multi-head attention. Otherwise, we again scale it. We just add this triangular matrices before to the scaled matrix before passing it to the softmax, so that the token that are in the future are masked and are not visible to the decoder at that point of time. Now let's write the code for this causal mask. Okay, this will be a very simple, straightforward method. We will call it create causal mask, and we will give it sequence length and device, like if it's on CPU or GPU, and we will just call mask equal to torch dot trill, basically the triangular matrix, and fill it with fill it with ones on the sequence length, and we will return the mask. So this is the simplest way to create a causal mask. One more thing that decoder mask need is the as mentioned in the paper is the padding mask as well. We will add that as well, create padding mask, and it is also very straightforward. We just have to create padding mask sequence and again the pad index, and we will give mask. Okay, AI is already doing the heavy lifting, so we will just, yeah, that is the right code. We will just add hit a tab. So basically it creates a padding mask where 0 is equal to masked, 1 is not masked. It is for all the shorter sentences. You add a pad token that makes them the same length, but we don't want the model to pay attention to the padding mask. So that's why we add this special token. It doesn't carry any real value or information. And now finally we can write the mask for the decoder. That is We can combine the mask and call it create decoder mask maybe, and it has a target tensor and a padding index. So we are just combining the padding mask and causal mask for decoder self attention. So it has the sequence length, which is of the size of the target, the target device. Padding mask, we just created the function for causal mask and padding mask, and we are just doing an AND operation on it to combine it. Yeah, so that's it. That's the mask multi-head attention, or the mask for the multi-head attention. We will apply it on once we write the whole decoder architecture. So for now, just this bit, like the what is the mask operation doing, that's what we discussed. So after the mask self attention, the next component the decoder has is cross attention block or component. Basically, the decoder has built a context aware representation of what it has generated so far after the mask self attention, but it still hasn't looked at the source sentence at all. It knows what it has said, but not what it was supposed to be translating. Cross attention is where that connection happens. Here's the key thing to understand about cross attention. The Q, K, V come from two different places, unlike self attention, where they all come from the same sources. Q comes from the decoder's output after the masked self attention step. So the query represents, given what I have generated so far, what do I need to look for the next? And the K and V, like the key and the value, both come from the encoder output, the rich contextual representation of the source sentence that the decoder produced. Think about why this makes sense. The decoder is essentially asking a question with its query. I have generated aap kaise so far. What part of the input should I focus on to generate the next word? The encoder's keys answer that question by saying, here's what each source token has to offer. And the encoder's value deliver the actual content once the relevant source tokens are identified. This is also why the encoder output is computed only once and then reused at every single decoder layer across all 6 decoder blocks. The encoder finishes its job completely, produces its output representation, and those same representation are plugged into the cross attention of every decoder layer. As you can see in this diagram as well, the key and value are coming from the encoder, and the query is coming from the previous mask self attention multi-head attention output. Another thing worth noting, because K and V come from the encoder, the cross attention has a different sequence length dynamic than self attention. The Q has shape of batch, target length, and dimension of the model, and the K and V have shape of batch, source length, and dimension model. These lengths can be completely different. Your source sentence can be 10 tokens and your target sentence can be 8 tokens. The attention score matrix ends up being target length in cross source length, meaning every decoder position attends over every encoder position. This is exactly what you want. Every output token can look at every input token to decide how much to borrow from it. When translating, how are you from to aap kaise ho? When the decoder is generating kaise, cross attention lets it look back at the full encoder output and decides that R in the source is the most relevant token to attend to right now. The alignment between source and target is entirely learned through training. The model figures out by itself which source words matter for which target words. So this is how the cross attention works. Here, as you can see in this as well, like it maps like which word is more useful for the translation. Now, since The rest of the step, like after cross attention, it's add and norm and feed forward, positional feed forward neural network, and then add and norm. This whole steps are similar to the encoder. So we have already discussed it and wrote the code for it, so we can just skip it, and we will just uh, go on to write the decoder, entire decoder layer. These cross attention and multi-head attention we have also already written. We have to just pass or tweak in some parameters, and we will get the result for it. So now let's write the decoder layer. Okay, we will again define a new class called decoder layer, and we initialize. AI did all the thing. Let me just check if it's correct. So okay, yeah, we initialize it with the D model number of heads, the dimension for the feed forward neural network, that is 2048, and the dropout rate. Then we create a self attention, that is multi-head, with the dimension of the model number of heads, dropout layer. We should call it masked self attention, and we then create the cross attention, initialize the cross attention with again the same parameters, like D model number of heads and dropout layer. There is again the feed forward and three add and norm layers, because in decoder we have three add and norm layers, normalized layers, and finally the dropout. And in the forward we just sorry in the forward we do the same thing. We calculate, get the attention weights, we add the dropout, and perform the add and norm for the first one. Then for the cross attention we do the same, and finally for the feed forward we are also doing the same. So this was a pretty simple decoder layer. Now let's create the decoder itself, because as you remember, a decoder also has 6 blocks in it. So we are going to club it now. After the decoder, oh, I missed one thing, that's why it was complaining. Masked self, this is a masked self attention. Yeah, okay, now it's fine. And let me check the rest of the code. Yeah, self cross attention is fine. Yeah, here, okay, here's the difference I forgot to mention. Like in cross attention we are giving like for the Q query we are giving the output of the decoder, like what we are getting in the previous after the mask self attention, and for the K and V we are getting it from the encoder output. That's why it's called a cross attention. Now we can move forward to the continue to our decoder layer. All right, in the decoder layer, it is again we have vocabulary size, dimension model, number of heads, dimension of the feed forward, number of layers, which is 6 in this case, and dropout rate and maximum length. Yeah, we call in the embedding the positional encoding layer, the 6 layers, and the normalization layer. In the forward, we embed the target sentence, and we add the positional encoding. Then we perform for each layer. We call the decoder layer and perform the task of decoding it. And next, yeah, and then we return by after applying the self.normal. So this was the simple decoder layer. Now we will focus on, so this is what we coded in the decoder part of it. Now we will look at the output, this output part of it, because it is a little different from the encoder. It has a linear layer, then softmax before it. Let's discuss this one next. Okay, the decoder's final output until here is a tensor of shape, batch, size, target length, and demodel. So for every position in the target sequence, we have a 512 dimensional vector. But what we actually need is an answer to the question, what is the next token, and to answer that we need a probability distribution over our entire vocabulary. Think about what that 512 dimensional vector actually represent at this point. It has passed through 6 decoder layers, absorbed information from the source sentence via cross attention, and build up a rich representation of given everything I have seen. Here's my current understanding in 512 numbers. But those 1200 numbers don't directly tell us which word comes next. They live in the model's internal representation space, not in vocabulary space. This is where this final linear layer comes in. It is a simple n-linear layer with the dimensional model and vocabulary size shape, a matrix of shape. The shape of the matrix will be 512 cross vocabulary size. If your vocabulary has 10,000 words, the matrix is 512 cross 10,000 in size. What it does is it projects that 512 dimensional internal representation into a vocabulary size dimensional space, producing a one raw score called a logit for every single word in the vocabulary. Logit is basically equal to like a decoder output multiplied by the weights of each vocab. You think of each row of weight of the vocab as a learned signature for a particular vocabulary word in the model's 512 dimension. The dot product between decoder's output vector and the word signature tells you how well the current state matches that word. High dot product, high logit, the model thinks this word is likely next. So as you can see in the in this diagram as well, that from 512 we split or make it into a linear number of linear layer with number of neurons equal to the number of vocabulary in the output set. So and this matrix is just these final vectors which we got out of the decoder stacked on top of each other after this part. Then after the linear layer, we apply the softmax to turn these raw logits into proper probabilities that sum to 1. Now for each position, we have a full probability distribution over the vocabulary. The word with the highest probability is what the model predicts as the next token at that position. One important note on when softmax is applied. During training, we never explicitly call softmax ourselves. Instead, we pass the raw logits directly into the cross entropy loss, which applies log softmax internally in a numerically stable way. Only at inference, we actually want to read probabilities or sample from them. So we apply softmax intentionally then. Finally, one optimization from the paper worth mentioning here. The weight matrix of this linear layer is tied to the embedding matrix. Remember, the embedding layer maps vocab size to the dimension model. This output projection maps the dimension of the model to the vocabulary size. They are exact transpose of each other in shape, and the paper shares the same weights between them. The intuition is that a word's embedding, how it's represented as input, and its output signature, how the model recognizes it as a prediction, should be related. And sharing weights enforces that while also cutting parameters significantly. Now let us combine all the code like encoder and decoder into a single transformer class. Okay, now let's put the whole thing together. We will create a class called transformer. Then again, it will have an dot module as inherited class. We will simply define the initialization function, which has source vocabulary size, target vocabulary size, dimension of the model, number of heads, dimension of the feed forward neural network, number of layers, dropout rate, and max length. We again call the constructor of the parent class, and we then initialize or instantiate encoder and decoder class, and finally the output linear class. Then in the method, before that, I think AI missed something here. Let me check number of heads, difference. No, it's fine. Okay. Now in the forward class, we will simply call the create for the source mask and the target mask by creating padding mask and creating decoder mask, and we will also get the output from the encoder and the decoder, and finally return the output in the linear. So as we have already written all those functions, we have to just call them and in the transformer itself. And one more thing here that was missed by the AI, like we also need one more function that is self dot init parameters. So this is a function for initializing parameters, initializing weights basically using Xavier uniform initialization. This is the standard initialization for transformers. It is important for training stability. So let me write this function as well. It will be dev initialization, and for each parameters we will, if the dimension is greater than 1, we will just simply initialize it using the Xavier uniform. And that's it. We are done with the transformers class. Next, what we will do, we will write the code for inference as well, like a simple short code for inference. Before that, I also want to discuss one small thing that we skipped on purpose, that is this right shift. So before we run the forward pass, we basically add a start of sequence a special token in the output training output code, training input code, input sentence. What this will do is, this is basically called teacher forcing shift, and it's one of those things that confuses a lot of people in the first time. So now look at what we are asking the model to do. When the decoder receives a SOS token or start of sequence at position 0, it should predict ARP like the first one. And when it receives ARP at position 1, it should predict cache like the second token, and so on and so forth. And like when we are done with it, at the end it should predict EOS, a special token, that is end of sequence. So target input is what we feed into the coder, and target output is the ground truth we compare the decoder's prediction against when computing the loss. They are the same sequence, just offset by one position. The decoder always receives the correct previous token as input. That's what teacher forcing means. and is asked to predict the next one. This shifting is why the sequence length going into the loss is target length minus 1 and not target length. We lose one token because there is no ground truth next token for the end of sentence position. So that's why we do this right shift. So now let's come back and write the inference part. Okay, now let's write our inference function. We will call it greedy decode, and it will have model source mask and SOS index, end of sequence index, and max length, and also the device. And the most important thing is at torch.nograd. This decorator at the top is important. During inference, we are not computing any gradients. We are just doing a forward pass to get the predictions. Wrapping the function with torch.nograd tells PyTorch to skip building the computational graph entirely, which saves significant memory and makes inference faster. Always, we should always use this during inference. Next, to write the first thing, we will use model.eval. This switches the model to evaluation mode. This matters because some layers behave differently during training versus inference. Dropout, for example, randomly zeroes out neurons during training, but should be completely disabled during inference. So every forward pass gives the same deterministic result. Calling model.eval handle all of this automatically. Then we next add the batch size, which will be the source size, last source size, and then next will be encoder output, which will be equal to model. We will just call model.encoder method with the source and the source mask. This runs the entire encoder once and stores the result. This is crucial. The encoder output never changes during generation because the source sentence never changes. So we compute it once upfront and reuse it at every decoding step, rather than wastefully re-encoding the source sentence on every situation. I think I misspelled. Oh yeah, it was helpful there. Next comes the decoder input. So for this we will use torch.full. Okay, I think AI is giving us the answer already. And this is batch size 1, SOS index, and torch.long and device. Okay, yeah, this is correct. So this creates the initial decoder input, a tensor filled with the SOS token ID. Shape will be batch size, 1. This is the seed that starts generation. The decoder sees SOS special token, start of sequence, and from that produces its first prediction. Then the next will be finished. That will be zeros, torch.zeros. Again, AI is helping us. The batch size, torch.bool type, and the device. Yeah, this is correct. So basically, this is a Boolean tensor tracking which sentence in the batch have finished generating. We need this because in a batch, different sentence may produce end of sequence or EOS at different steps. we don't want to keep generating tokens for sentences that are already done. So that's why we need this tensor. And then we will start with our generation loop for step in range max length. Inside the loop, each iteration represents generating one new token. First, we create a fresh causal mask for the current length of decoder input as we append tokens. The sequence gets longer, so the mask grows with it. So let's write the mask for it, which is target mask. Okay, AI has again provided, but we will use only the causal mask in this case. Yes, causal mask with the decoder input size and the device. Oh, okay, and then we get the decoder output. Decoder output with the model.decoder, decoder input, encoder input, target mask, and source mask. I think first will be the source mask, then the target mask. Let me check the signature. Yeah, okay. First is target mask, then the source mask. Okay, I was wrong. Okay, so basically this model.decode runs the full decoder stack and produces shape of batch, current length, and dimension of the model. But we only care about the last position, that is decoder of output in the slice with the slice of -1, because that's the position that has attended to the entire sequence so far and is predicting what comes next. All earlier positions are already decided. This gives us a shape of batch, dimension of the model. Next, we pass in for this it will be the logits like what I just explained. We just want the last token that it has generated. So we, as I said, we just want the last position, so we are adding this slice, and after that we pass it through the model dot output linear projection. Model dot oh yeah, I gave it this the wrong. Output dot projection. It has to be projection. I think it gave us the output linear. Oh, okay, fine. The name is output linear. Yeah. So basically, is to get logits over the vocabulary. Then we have the next token as logit.argmax, and we are in this case we are going to keep dim equals to true. This is basically this picks the single highest scoring token for each sentence in the batch. This is the greedy choice, and keep dim equals to true keeps the tensor as batch 1 rather than collapsing to batch 0, which we need for the next line. After that, we get apply torch.concatenation to the output, not the input. Yeah, sorry. We apply to input. After that, we apply the torch.concat. Basically, appends the newly generated token to the decoder input along the sequence dimension. So In the next iteration, the decoder sees one more token and can attend to it when predicting the following one. And finally, we write finished this updates the finished tracker. Any sentence that just produced end of sequence gets marked as done. The this or and equal to, or you can say pipe and equal to, is a bitwise or assignment, meaning once a sentence is marked finished, it stays finished regardless of what tokens come after. And once we have all the tokens are done processing, we break the loop and we return the decoder input. This will be of size batch comma generated length, and that's it. That's the inference part done. And I think we are done with the whole architecture. Yes, we didn't miss anything. If you want to go deeper, I would recommend reading the original paper. The next step would be to train this model on an original translation dataset like WMT, which is what the paper used. For that, you would want a GPU and a good BP tokenizer. The full code of this video is linked in the description. Thanks for watching. See you next time.